Let's do a real quick review on specific heat. And again, a lot of y'all have had no problem with this, but some of you still struggling with it. So the idea with the specific heat is it is a characteristic of any kind of substance, and it has to do with, if you want to think of it, its ability to absorb energy. And the way that we measure this a little bit too is it depends upon how much of a temperature change we have. And this is where when I used the term capacity originally, that's when I talked about the idea of having a big stadium versus a small stadium, because these two things have different capacities to them. And if we use the idea of a human being as being as a unit of energy, then we can kind of get an idea of what a large capacity versus a small capacity would be. Because if we have individuals going in to each of these buildings at the same rate, well, the one with the really small capacity, this guy over here, it's going to get full much more quickly than the larger one because it's able to hold more. And if we think of full as a certain temperature, say 100 degrees, then the idea is that this small item, the small capacity over here, would get full. It would get to 100 degrees way faster than the large capacity item that's over here. Now, it simply has to do with some of the characteristics of the molecules and matter itself, which is beyond the scope of what we need to worry about. Mainly, we just need to worry about whether or not we understand how to compare values and kind of what characteristics things would have if they had a high capacity or if they ended up having a low capacity. So let's make this a little bit more specific to science. Let's say we take a couple of objects. We take take a glass of water, and we take just a big hunk of metal. And if we put both of these on the stove at the same temperature and give them the same amount of energy, what's going to happen is we're not going to experience the same temperature change. Okay, the temperature changes are not going to be the same with both of these. We're going to expect, hopefully we know in our just experiences, that the metal's temperature is going to increase faster. The water, on the other hand, its temperature is going to increase, but it's going to do so much more slowly. So thinking back to my last drawing with the stadiums and the capacity, this would help me to think that if this one's going to be filling up slowly, if its temperature is rising slowly, this is generally an indication that this substance, the water in this case, would have a higher heat capacity than the metal, because the metal is going to heat up really quickly. Its temperature is going to get full, if you want to think of it that way. Effectively, it won't be able to hold any more heat. There comes a point where we're going to be adding heat to it, and the temperature is not going to increase because it's just not going to be able to hold any more energy. It's already as hot as it's going to be able to get, or its temperature is going to be exactly where it is. So again, we can see these effects in different substances, the rate that they heat up. So kind of the rule is for something that if something has a high capacity, it's going to be slow to change temperature. If something has a low capacity, it's going to be fast to change temperatures. And I know that's almost backwards. I think some of y'all are still having a problem with that. That you think if it's got a high capacity, then it's going to heat up really fast. But no, that's not the case. If it's got a high capacity, it would actually heat up really, really slowly, because just like the giant stadium that has a high seating capacity, it's going to be slow to fill up as well. So finally, one of the things we're supposed to be able to do is to, in addition to comparing materials, being able to compare the materials based upon the specific heat values that are given to them. And so our specific heat values, substances have a value. It's kind of like when you guys had earth science and you talked about the density of materials. Gold has a certain density, silver has a certain density. Every material has a density to it, and it's just a characteristic of that particular property. And the same thing is true of specific heat. In this, we're able to measure what the specific heat is of something. So specific heat specifically is joules. Remember, all right, so joules are energy. So we got joules per gram, and then there's a Celsius change here. So this is literally, it's the amount of energy. It's the amount of energy needed to increase the temperature of 1 gram of the substance by 1 degree Celsius. And again, we don't need to memorize that, but that's what this unit is here to tell us. So for example, with water, its specific heat is 4.18. So it needs 4.18 joules of energy in order to change 1 gram by 1 degree Celsius. Okay. Whereas if we go to the other end with lead, lead only needs 0.13 joules of energy to change 1 gram of it by 1 degree Celsius. So in other words, if we had 1 gram of lead and we had 1 gram of water and we wanted to change the temperature of each of them by 1 degree, then we can't accomplish that by adding the same amount of energy, because the water needs 4.18 joules of energy and the lead only needs 0.13. So once we add 0.13 joules to the lead, we will have accomplished our 1 degree. If we add 0.13 joules to the water, we're nowhere near the amount of energy needed to raise that temperature. So we would need to add another 0.13 and another 0.13, and we would need to continue adding it until we got all the way to 4.18 joules. That's the amount of energy that would be required to change its temperature. So if we add the same amount of energy, this one's temperature is going to go up way faster than this one's going to go up. So this one's not going, if we added 0.13 joules, this one's going to go up by 1 degree. This one's not even going to go up by 0.1 degree. So again, what we see is the higher the number is, the slower it's going to be to heat. All right. The smaller the number it is, the faster it's going to be able to heat, or the faster it's going to be able to change its temperature. All right. So again, we can compare numbers to get an idea of whether or not something's heating up quickly or something's heating up slowly. If we were to graph this and look at it on a graph, what we would see is that if something's heating slowly, like the water, what we would see is it would change temperature fairly slowly. It would be a flat line. So as we add energy, and if this is temperature, the water is going to heat very slowly, whereas the lead's temperature is going to increase very rapidly. All right, so again, this would be fast heating, and that means low capacity. The water, on the other hand, slow heating because it's a flat line, and that tells us that it's a high capacity. And the last thing about all these is we tend to use some vocabulary words to talk about whether or not something heats up quickly or slowly. These things down here at the bottom we tend to refer to as conductors, because energy is able to move through them very, very quickly, whereas these things up here at the top where the energy doesn't, we tend to refer to as insulators, because the energy does not move through these. And we can kind of get a relative idea. Sometimes we had an experiment that we were supposed to do to be able to investigate this, but you can also do it with your hands, because our body heat is about 98 degrees, and the things that we touch, when we feel something in the room, if it feels cold, even though it's the same room temperature, that's just an indication that it's able to pull the body heat out of me. So around me right now, there's a metal piece on this desk. If I grab this metal, it feels cold, where if I touch the tabletop, it doesn't feel quite as cold. And definitely if I touch my sweater, which you can't see here, if I touch my sweater, it doesn't feel cold at all. But these two things have been sitting here in this room the entire time since yesterday. So there's no energy source to them. These are the same temperature. My two hands are the same temperature, but if I touch them, they don't feel the same temperature. And this one feels cold. And the reason it feels cold is because my hand is losing lots of energy really, really fast. And so when we touch something and it feels cold to our touch, that's usually an indication that we've got something down here on the bottom part of this scale. Because if it's pulling energy really quickly out of my body, that means that that substance doesn't really have a capacity for very much energy. It's going to fill up very, very quickly. Whereas my sweater, on the other hand, would maybe be up here because it has a large capacity for heat. It can absorb a lot of energy and doesn't change its temperature. And because of that, it's not going to pull the energy out of my body. So sometimes we can just get an idea, relatively speaking, of what might have a higher heat capacity just by touching something. So oftentimes if we touch something and it feels cold to our touch, now if you bring something out of the refrigerator, that's different, but I'm just saying at just a normal room temperature, if we're touching two different things, oftentimes if something's a conductor, it's going to feel possibly colder to our touch, whereas something that's more of an insulator is going to feel warmer to our touch. And it's not because they have a different temperature, it's because of the energy leaving our body. And so these things up here don't really pull the energy out of our body. These things down here will pull the energy out of our body. And if we hold on to them very long, we're going to start feeling cold because we're losing so much energy out of us.